Okay, hello. Let's go ahead and get started. I want to do a problem from section 4.7 regarding optimization. Let me show you kind of quickly here something that I've got up on my calculator at the moment. Let me get that, share the screen. And what I've got is this. Here's a problem that I want to look at. It's an optimization problem. This example one down here, it's called maximizing an area. And what we've got, a farmer with 4,000 meters of fencing. So he's got some fencing in hand, a set amount of fencing. He's enclosing a rectangular plot that borders a straight river as shown in this figure here. Here is the river, and here is the area that he's hoping to enclose. It's rectangular, and the fencing is needed on 3 sides and not the river side, okay? He does not fence the side along a river. What is the largest rectangular area that can be enclosed? So the idea is we've got 2 different equations of concern here. We've got an equation regarding the amount of fencing he has, and I assume fencing he or she has, the farmer has, and the area that's hoping to be maximized. So let's go to my iPad and let's go to, I want to figure this problem out. Remember what's happening. The amount of fencing is there's 4,000 meters, 4,000 meters of fencing. Okay, so the 2 equations are, we've got the amount of fencing involved. And the amount of fencing, you can see on the diagram, I don't know if you noticed that they had an X and X and a Y there. That could have been Y and X, or you could have done a bunch of different letters, but these 2, it's rectangular, so these 2 sides have the same length. And therefore, we've got the amount of fencing is 2x plus y. And this is one of the equations that we're dealing with. And this is the constraint equation because we're told we've got a limitation here. We've got 4,000 meters of fencing, 4,000 meters. That's the equation that we are concerned with. That is one limitation we've got to work with. The other equation that we're trying to maximize is the area of that region. So the area of this region inside here, you can see it's rectangular, therefore it's equal to x times y. So that is the other equation of concern. And this is the one we're trying to maximize. So this is the one we want to get in one letter if we can. What allows us, by having a constraint equation, we might call it, is we can solve for one of the letters and plug it into the other, substitute it in the other, and just have one variable in the area equation to work with. And that means we can take the derivative and set it equal to 0 and find the situation out. So let's take a look at this. So in this problem, the 2x is here and the y is here. And if you're wanting to solve for one of the letters, the most straightforward one is just get the y by itself. It's already y. You could solve for x, but you got to divide by 2, and that makes it a little more complicated. We can just solve for y. Got to subtract the 2x, we get 4,000 minus 2x. And now, if we substitute this in here, we'll just have x's, and then we can have a function in terms of x, take the derivative, set it equal to 0. So we end up with the area is equal to x times 4,000 minus 2x. Right? Simply multiply that out, we get 4,000x minus 2x squared. So our area function is actually, turns out to be this. And we're trying to maximize that, all right? Notice what the shape is of what is the graph of that function. You can see that it's an x squared. Squared is the largest exponent. Therefore, it's a parabola, right? And it's got a negative in front of the x squared, so it is an inverted parabola. And the max, it makes sense. We could calculate the max because the max is going to be at that peak, and that is where the slope is equal to 0. Therefore, take the derivative, which is the slope, set it equal to 0, and find what x causes that to be 0. So we got to take the derivative of this function now. So we end up with a prime, and we can call this a prime of x. We could have labeled that a of x since it's a function in terms of x if you wanted to. A prime of x equals now, derivative of 4,000x is 4,000. And the derivative of the next term, we bring the 2 down, we get negative 4x. So one way to write that would be 4 times 1,000 minus x. Now we set that equal to 0 because we want to find out where the slope is equal to 0. So the 0 equals 4 times 1,000 minus x. Therefore, in order for that to be 0, 1,000 minus x must be equal to 0 because 4 can't be equal to 0. So it turns out that x is equal to 1,000. Remember now, x equals 1,000. That's not the answer to our question. We solved this and we got x equals 1,000, but it's asking what is the maximum area? And the area requires you to multiply the x and the y. Or we could plug x back into this function as well, but let's go back to x equals area equals x times y. That means we need y. So notice we did have y. We solved for y here in order to substitute it in. So if we plug 1,000, y equals 4,000 minus 2 times 1,000. We could calculate y, which gives us 4,000 minus 2,000, which equals 2,000. So we have y equals 2,000, x equals 1,000. Therefore, that maximum happens when x is 1,000. That means y must be 2,000. Therefore, the area is equal to xy, which is equal to 1,000 times 2,000, which gives us 2 and 6 zeros, which is 2 million. And it was given, the original function was given in fencing, was given in meters. So the answer is in area, so it must be meters squared. So that max area that you could get out of the 4,000 meters of fencing is 2 million meters squared. That is the solution of the problem. Notice the sequence. We had to develop 2 equations. One was for the area, which we're trying to maximize, and the other was a specific part of the problem that had a limitation to it. It had a constraint given in the situation, and that allowed us to solve for one of the letters. That constraint allowed us to solve for one of the variables and substitute it into the original function and get the function to just be in terms of x, and that allowed us to take the derivative, set it equal to 0, and find out where it occurred. So follow that process, get the gist of the idea. That's the general format for when you're doing optimization problems, okay? And we'll talk to you a little bit, do another problem a little bit downstream. Thanks. If you got questions, make sure you get in touch with me during office hours, and we'll make a connection and clarify things, all right? So I'm going to stop and see you a little downstream.